All right, hello everybody. Shall we get started? Okay. You might have noticed that there is a new project posted as of, I think, yesterday or today morning. Project number 3 on splines, where you'll get to solve some example linear systems. Take a look at it. Let's do again the next Tuesday. Let's get it right this time. But it's midnight, so it's like almost Wednesday. So today we will do elementary group theory and explain how does it relate to matrix operations, because it has immediate implications to the matrix properties we talked about before. So maybe let me start right there. What did we talk about before? We ended by discussing the matrix transpose and inverse. So let me just clarify a few things related to matrix transpose and inverse to calibrate my setup. Actually, let's sort of contrast them, because it's sort of interesting to transpose and inverse. What are the similarities and what are the differences between the two? Better? Okay. So if I want to talk about a transposition, I can have an arbitrary matrix. That means n by m matrix. It can be rectangular, right? And if I transpose it, I get, I won't even ask because it's so obvious, m by n matrix, right? And sharp episode 1 is better. Okay. And the element on row I and column J of the transpose matrix happens to be the same as the element on row J and column I of the original matrix. That's how transpose is defined, right? So interchanging the role of rows and columns. Very simple operation, right? And I think I showed you before a graphical proof of this property. So how does the transposition relate to multiplication? So AB transpose is the same as B transpose A transpose. So the most important thing is to remember that the order of the matrices flips. Okay, so let's now look at inverse, which is sort of similar operation. So the first difference is right here, right? Can I be inverting arbitrary matrix right here, like here, n by m matrix? What shall I write here? R, we are looking at real matrices. N by n, right? So inverse is only defined for square matrices, or only the case when n equals m. So that's one important difference there. So obviously then the inverse is also a square real matrix, also an n by n matrix. And how's the inverse defined? Well, we defined it as A inverse must equal identity. So in other words, A inverse is such a matrix such that when multiplied with A from the right, it gives me back identity. Of course, by identity I also mean n by n identity, right? That makes sense. Otherwise, types wouldn't even work out, right? And we have, I think, I also showed last time, I think that's what we ended with, was the rule for the inverse of the matrix multiplication. So remember what it is? The inverse of A times B. It's very similar. It's basically this, right, with inverse. So it's B inverse, A inverse. And the proof of that was very simple. Just use the associativity. No problem, right? So this looks, I mean, except for the difference. So in case I was talking about square matrices, in case I was transposing square matrices, then these things are really related, right? You see that it has the same structure, that it flips the matrix multiplication, the order in which I'm multiplying the matrices. And there is actually an important class of matrices where inverse is exactly transposition. You know what these matrices are called? We had them before. That's the orthonormal matrices. So let's take a look at how does it work for orthonormal matrices. So it's good to realize that. From graphics, you definitely know this. So the group, this is what we'll be talking about mostly today. The group of orthonormal matrices is denoted like ON. Like don't confuse it with like the linear asymptotic complexity. This means the group of orthonormal matrices of size n by n. Okay. And how was, again, let's remind me, how was orthonormal matrix defined? So if I had a matrix from ON, that means that it's an n by n matrix, right? But not just any n by n matrix. So if I write the rows the matrix like this if I denote the rows as A1 to AN. So for the matrix to be orthonormal, what must be true for the rows of the matrix? Now you need to remember how our orthonormal matrix is defined. You can also, like, these questions I'm sort of asking, you can think of it like light preparation for the midterm, all these exams. Somebody was asking what will be in the exams and so on. Like, there won't be that basic questions, but you will need to know these things to construct answers to more complex questions. So orthonormal matrix was defined, if I denoted the rows like this, then the matrix is orthonormal if and only if AI transpose AJ equals delta IJ. So let me explain this a little bit in case it's confusing to you. So AI transpose AJ, the last time I explained that this is equivalent as saying AI dot product AJ, right? Thanks to the transposition, I don't really need a special product for special symbol for dot product anymore, so I'll actually get rid of it, because later I will use this dot for like a group operation. So let's forget about the notation of the dot product, and just remember that this AI transpose AJ means the dot product between AI and J. Yeah. And you know this delta IJ, that's the Kronecker delta. That basically means that it's 0 if I is different from J, and it's 1 if I equals J. Okay? In other words, if I dot the row vector of it itself, I get 1. If I dot two different rows, I get 0. That's just, I'm just reminding you the definition of one orthonormal matrix, something you absolutely must remember. And why I'm bothering you about this, again, we already had orthonormal matrices before, because here is the cool thing. Let's say that this is my matrix A. Let's write it again here. And let's see what happens. Or maybe I could ask this way. Do you know what is the inverse of this matrix? I guess you only know the answer if you have already seen it before. The cool thing about orthonormal matrices is that the inverse is very simple. Not exact, almost. It's a good guess. The suggestion was itself, so that's an. Save this for later. That will be the right answer. Transpose, exactly. Because if I do a transpose of A, that will look like, so I interchange the role of rows and columns, right? So these guys become columns. Transpose is the right answer here. So this is my AT. So what do I get here? This is an n by n matrix. This is another n by n matrix. So the result definitely is going to be an n by n matrix, right? What's going to be the first element? A1T A1, so that's A1, that's 1, right? This element will be A1T A2, right? So 1 is certainly not 2, so that's 0, right? And so on. So what you get here is perfect identity matrix, right? So this is identity, n by n identity. And of course, if I have a matrix which multiplied from the right that my original matrix gives me identity, well, then this matrix is called the inverse, right? So in this case, I have A transpose is the inverse of A. So that's true for all orthonormal matrices. Very useful. If you know your matrix is orthonormal, computing the inverse is a piece of cake. All you need to do is transpose it. And yeah, here you can sort of see that this works beautifully. They must be square, of course, for this to be the case. So we had some example of orthonormal matrices. Rotations, right, are orthonormal. So if I have a 2D rotation, cosine theta, sine theta, you know what, let me do it on another paper so it doesn't get too messy. So let's take a rotation, 2D rotation. 3D will work as well, but it's easier to explain it. 2D minus sine theta and cosine theta. So this is rotation about angle theta, right? And if I invert it, now you can, I mean, you probably knew the answer anyway, right? But here you can basically just blindly transpose it, right? Or reflect this matrix about its main diagonal. So I'll just put sine here, minus sine here, and the cosine stays here. So I just transposed it. The other way you can look at it is that this is basically the rotation about angle minus theta, right? Because we know that if you do cosine of minus theta, you get cosine of theta, the minus disappears. And if you take sinus from minus theta, you get minus sinus theta, right? It's due to properties of the trigonometric functions. So yeah, so here in the case of rotation, it totally makes sense, right? Because if I transpose it, I end up getting the matrix, the rotation with the negative angle, which clearly is the inverse transformation there. So in this case, it totally makes sense. By the way, what would be, can you give me an example of an orthonormal matrix which is not a rotation? Slightly tricky question. It's good to think about that. So certainly all rotations are orthonormal matrices. I guess I didn't really define it properly. But you can think about a 2D example. Here is a simple example. Think about this transformation in 2D. -1, 0, 0, 1. What does this transformation do on an example of a house? If I have a house and it has a door here, this transformation does what? Reflection, right? Like mirror about the y-axis, right? So x gets mapped to -x. So this house, the door is important here. The door will get mapped here. I guess I could do a chimney. So there's a chimney. So you can see it's mirrored, right? That's what this transformation does. It's perfectly orthonormal, right? If I dot product the two columns or two rows, doesn't matter. Actually, later I will show you that it doesn't matter if I talk about rows or columns, by the way. So if I dot product them, either way, I get 0. If I take the norm of each row or each column, obviously 1, right? Perfect orthonormal matrix. Nevertheless, there's no way how you could take this house and rotate it onto this, unless you went up to 3D, right? But we are in 2D. Going to 3D is not allowed. That would be we are talking about 2D transformations, right? So this is an example of a reflection, and reflection is an orthonormal transformation represented by an orthonormal matrix, which is not a rotation. So later we will see that this is actually characterized using the determinant. So there is actually, let me just give you like a sneak peek. Orthonormal matrices come in two flavors. One is rotations. The other one is reflections. And the way we decide is by looking at the determinant. So I know we haven't discussed about determinant yet. We will discuss about that properly later, but let me just give you a quick preview, because the determinant tells you which of the two cases it is. The determinant 1 means it's a rotation, determinant -1 means it's a reflection. If it's an orthonormal matrix, then the determinant can be only 1 or -1. So what is the determinant for a 2x2 matrix? If I have a 2x2 matrix, then the determinant is quite simple. So determinant in general is a function from n by n matrix, which assigns it a scalar. And for a 2x2 matrix, it's quite simple. It's just AD minus BC. That's what the determinant is. So I guess we could test it here if this rule really applies. So what's the determinant of this matrix, or this? Doesn't really matter, both are rotations. So let's see. What is the determinant of this matrix? Just use this formula, right? This is my AD, this is my BC. 1, right? This is cosine square minus minus, aka plus sine square, that's 1. Right? And the determinant of this matrix, that's even simpler, -1, right? So I was not kidding. Indeed, if the determinant is -1, it's a reflection. If it's +1, it's a rotation. So the determinants of the detector of what case are we dealing with. Okay, so this was to elaborate on the transpose and inverse. So on the case, I guess my point here was that on orthonormal matrices, either rotations or reflections, transpose for a square matrix is exactly inverse. Okay? It's good to remember that. And now we can jump into the group theory. So as a quick motivation, one of the results we will get from the group theory will be, I define the inverse using right multiplication, right? I said that the inverse is such a matrix when multiplied with A from the right. This is my inverse, so it's multiplied from the right. Because in general, it's not true that AB would be BA, right? Matrix multiplication is in general not commutative, right? But it turns out that in the case of matrix inverse when if the two matrices multiply to identity. In this case, actually, it is the case. So in this case, A inverse is the same as A inverse A. And we will get this just from the group theory. That's something more general than matrices that applies to more objects than just matrices. Actually, matrices are a special example. Invertible matrices are a special example of a group. So it makes sense to look at group theory in full generality, because then it applies to other objects too. It's usually a good idea to think as general, even in programming. It's good when you are like writing a code or something. It's good to think as general as possible, unless it costs you too much. So if you don't have to pay extra for it, for extra generality, then just make it more general, right? Maybe at some point it will be more useful. In groups, that's definitely the case. Have you had some groups before, some group theory type of business? So some of you did, some of you didn't. That's it's always the case here, so hopefully we will find a way to make everybody somewhat happy. So let's look at the definition of a group. So if you remember the definition of a vector space, this is a similar type of definition because we are talking about some algebraic structure. And in general, all these algebraic structure, they consist of a set. So that's just a set of some elements. Sometimes we call them numbers because we can compute with them. But they don't have to be numbers. They can really be whatever, elements of a set. And it becomes an algebra if we endow it with a group operation. So in this case of groups, in the case of vector spaces, we had like this vector addition and vector scale multiplication, right? In the case of groups, we have this group multiplication operation denoted as a dot. So don't confuse it with the dot product. This is something much more general than that. This is a general group operation. So dot product doesn't exist anymore. Just scratch that definition. And just like we had in vector spaces, there is a laundry list of properties, which is actually not that long in the case of a group, that must be satisfied so that the set and this operation define a group. Okay? So what these properties are, the first one requires, so if I should draw it like this, if my group is like a set and there are some elements, I can have finite or infinite groups. So if this is like a finite group, and the first property says that if I take any A, so let's say this guy is A, and any B from the group, then the matrix, then the group multiplication, the multiplication operation in the group produces some C, which is also in the group. So if my A times B is C, then the C is also inside the group. I guess I could say, if you wonder about the type of this group operation, that's a function that maps from G and G to back to G. That's basically what the closure means. I like to write the types of things. So this basically means that if I multiply two elements from the group, I will not run out from the group, right? So that it's self-contained or closure property. By the way, it's in general, again, it's known, it is not general in, it's not true in general that A times B would be B times A. It doesn't have to be commutative, the group, in general. There are special types of groups which are commutative, so where this is actually true, they are called abelian groups, and some groups work like this. The most interesting groups are not commutative. So in all groups, we will require associativity. So that's similar to what we saw in matrices, right? Here you might start seeing how it maps to matrices. So associativity simply means that for any three elements, it doesn't matter if I first multiply B with C and then with A, or if I first do A times B and then times C. So you can, that basically means that if you have some sequence of multiplications, it doesn't matter in what order you write the brackets. And final and most important property of a group is that you have the identity and inverse element. So the identity, that's denoted as this little lowercase e thing. So that's an identity element of a group. And identity means that when it's multiplied with any element of the group from the right, so A times E, it gives me that element A back for every element of the group, okay? So that's basically like my one, right, or identity matrix, if you want to relate it to something you already know. And final property related to the identity element is that for every element, I have an inverse. So inverse is another element, inverse of that element is another element of the group. So it's also inside, it's also closed. I don't have to go somewhere outside to borrow an inverse. And it's true that A times A inverse will give me back the identity element. Yeah, something wrong with that?
No, just what's an example of an identity that only works like from the right?
That's an excellent question. In a little bit, I will show some like basic theorems. And one of them will be that there is no such thing, that there is no difference between multiplying from the left and from the right. The beautiful thing is that those are the necessary defining properties, and all these other properties we can derive from these group axioms just by logic. That's actually what I'm gonna do next. I'm gonna derive these basic properties. Okay, that's the nice thing, right? You just sort of postulate like few axioms. That's your definition of a group, and then you scratch your head, and then you think what other properties follow from this, right? And the reason why we think about it on this abstract level is that there are tons and tons of examples of groups you encounter if you look for them. And then all the theorems we have derived for groups, once you have checked that all these properties are satisfied, then all the theorems will apply. And we'll be particularly interested in matrix groups. And I will get to it. Okay, so remember that this lowercase e is the identity element. So right now I just define multiplication from the right, yeah?
What is this symbols before the letters?
You mean this?
Yeah.
Oh, this means for each. Sorry, I was taking this for granted. This is from mathematical logic. Those are the mathematical logic or formal logic, I guess. It's been a while since I studied this, but that basically formalizes the rules you apply to do proofs in like a formalized way. This symbol means for each A and for each B in G. Okay. The other symbol, this is exists. So it means for every element A, if I translate it from like logic symbols to English, it means for every element A in G, in the group G, there exists an inverse element, which is denoted as A inverse in G, such that this is true. Okay. I guess I could write it probably like better, more neutral if you want it to be like really kosher, I guess. You could write it like this, right? So we don't give any special meaning to this power. It's exactly the same thing, but I just avoid the symbol to -1. But that's how we denote it, right? And this says it always exists as it, and it's in the group. Okay? Yeah, thanks for asking. It's always good to clarify this. It's the advantage of coming to the class as opposed to watching it online, where you can't really ask interactively, right? Okay, so I claim that groups are important. Well, they are important because there is lots of them. So let's take a look at some examples. We'll just look at toy examples. There is tons and tons of examples of groups, and like mathematicians study their properties and how individual groups are related. Let's look at the simple examples, but probably we'll get an idea. So I guess one of the most basic examples is an abelian group, commutative, where I take all integers with the operation of addition. So by all the integers, I mean -2, -1, 0, 1, 2, and so on, right? On both ends, I go up to infinity. I say that plus is my group operation. That's my group multiplication, I guess. Maybe I shouldn't be calling it multiplication, but group operation in general, if you will. So what is the identity element here? That would be the, yeah, that would be that, yeah, right, exactly. That's the right thought process you should go through. Like your instinct tells you 1, but then your brain says, wait a second. 0, right? So the identity, so here the E is 0, because if I add 0 to everything, I just get that back, right? So that's my identity element. And what is the inverse? A inverse here. It's also simple, right? So I need to, if I give you a number, you need to give me another number, such that when I add them together, I get 0. It's not very difficult. That's called negative or minus, or multiply by -1, right? I guess minus A. That's my inversion in this group. And it's an example of an infinite group, right? Because they are all integer numbers are there, including 0. Okay? And it's an abelian group because in this case, of course, A plus B is b plus a. So in this case, we do have commutativity. That's a very simple group, and not much going on here. Now here it starts getting a little more interesting. So the second example is the set of all real numbers except for 0. And the operation is multiplication. So I guess I could write it like this: the set of all real numbers except for 0. Or if you will, like entire real line, but I take out the 0. And my group operation is just the standard multiplication of real numbers. So what is the identity element here? Now your intuition is correct. Yeah, here identity is 1, right? And the inverse, of course, is what? Maybe someone.
Fraction.
Exactly 1 over a, right? That's exactly why I had to take out the 0, right? Because for 0 I would be stuck here. But how would I invert the 0? It's no good way to invert the 0. So that's why I take the 0 out of it, and now I have a perfect group, right? I guess you could also like verify all the other properties, but sort of obvious that if you multiply two non-zero numbers together, you get a non-zero number 2, right? And associativity follows directly from associativity of multiplication of scalars. So it's not even worth talking about it. Everybody got it? So the final, or not final, third example, I have a few more in my back pocket. Here is a little more exotic example. This will be a finite group. So both of these examples, they have infinitely many elements, but there are also groups which are, by the way, quite important, like in cryptography, that only have a finite number of elements. So this is an example which says the set is all n-bit numbers. So like, let's say n is 3, and I have n like this. So these are my examples of n-bit numbers, 3-bit numbers in this case. How many elements do I have? How many n-bit numbers? What is the size of the group? In this case, it's 8. Yeah, and if it's n in general, 2 to n exactly. So how do I define the group multiplication here? So here I say it's the XOR operation. Does everybody know XOR? Let me explain what is XOR. So this is the, so if this is bit x, this is bit y, then x XOR y is this. So if I have 0, 0, 0, 1, 1, 0, 1, 1, so this is 0, 1, 1, 0. Okay? So XOR is an operation on 2 bits, which gives me this bit back. Okay? And by XORing the binary numbers, I mean XORing them 1 bit at a time. Does everybody, is this obvious to everybody, or shall I explain some more? Okay, sounds good. So if I do this, let's stick with the n equal 3 example. Why not? So what do you think is the identity element, the E here? So that must be something such that when I XOR it with any binary number, I will get that number back, right? Yeah? Yes, exactly. So if I have just n equal 3, that's all zeros, right? Why? Well, because think about it. If I XOR 0 with 0, I get 0. If I XOR 1 with 0, I get 1, right? So if I XOR anything with all zeros, so let's do like, I don't know. It's sort of silly, right? But let's look at it. So if I XOR 1 and 0, 1, 0 and 0, 0, 1 and 0, 1, right? So I get the same thing back. Now, what will be the inverse? So I have a 3-bit number, and I need to come up with a different number such that when XORed with it gives me all zeros. So the hackers, do you guys still program in assembly language and use XOR? Some of you do, yeah?
The inverse of any number in binary set n is
Itself,
itself.
yes. That's the cool thing, right? Like this definition does not prohibit that the A inverse be exactly A, right? Why not? If it works, in this case it works, right? Because if I just XOR thing with itself like this one, because 1 XORed with 1 gives me 0, And 0 XORed with 0 also gives me 0. So this indeed will give me always all zeros. That's my identity element. So this is my inverse. So indeed, this is a group. I don't know if you remember this. There used to be, like in assembly language, there was this XOR operation. If you wanted to store 0 somewhere, it used to be more efficient to write this, like a register. Does it tell anything to any of you? Just like a weird flashback. I guess I'm just showing my age at this point. This was just like a trick in assembly language to put 0 to a register, because storing the 0 as a value would take some memory. But instead you can just XOR the thing with itself, the register with itself, just running the operation without using any data at all. So that used to be like the, I guess, old school assembly language trick. And maybe it still applies, I don't remember. I don't follow this anymore. Let's look at a few more examples of groups. I just want to give you, I guess, 2 more examples. Here is an interesting one. So multiplicative group of integers modulo p, where p is a prime number. So let's look at this one, make it more specific. So I'll say that my elements are just 1, 2, 3, 4, and that my a dot b will be just a regular multiplication but modulo 5. So note that 5 is a prime number, and I have all numbers from 1 to p minus 1, so 5 minus 1 in this case. So this is an example of a multiplicative group. Well, the multiplication is modulo some prime number. These groups are, by the way, very important in cryptography. Well, not that small, right? But when the prime number is really huge, then it leads to some cool number theory problems which are being used in like public key cryptography, if you know RSA and that sort of stuff. This is like the baby steps there. So what do you think is the identity element there? I guess that's easy, right? Your instinct is correct. The modulo doesn't matter. If I multiply it with 1, I'll just get something between 1 to 4. So that's just 1. And the inverse, well, let's look at the inverse. So inverse of 1 will be 1. Inverse of 2, I guess the easiest way to find it is just by experimenting, right? And so let me just write it and then we can discuss it. Inverse of, so why is this true? Well, let's see. If I multiply 2 by 3, I get 6. Modulo 5 is 1, right? So that means that 3 indeed is the inverse of 2 in this group. And again, 3 inverse is 2, because again, 3 by 2 is 6, modulo 5, 1, right? And 4 by 4 is 16. So 4 by 4 in this group is 1, again. So this is an example of a multiplicative group. Oh yeah, and final example, which we will then study in more detail, would be all n by n invertible matrices. I think I'll get to it on some later slides, so we can just proceed, and then we'll talk about the matrix groups later. So that's actually why I'm bothering you with groups here, because then orthonormal groups, permutation groups, all square matrices that are invertible, they also form groups. And there is, if you study applications, even like areas like chemistry and so on, just run into groups like all the time if you look for them. And if you look for them, then you realize that there is a group structure that immediately tells you that this body of knowledge about groups applies. So what body of knowledge I'm talking about? I'll just really scratch the surface, and I'll just prove some very basic properties of groups. I think that's, well, that's not exactly what you were asking about, but it's related to it. And it's related to how I motivated it by saying that AA inverse is the same as A inverse is A inverse times A, right? So here we can prove it in general in any group, just from the group axioms, okay, from the defining properties of a group. So what I'm gonna do here. So the theorem says that if E is an identity element, so identity element was defined such that if I multiply from the right with any element, I get the same element back. That's how it was defined, right? And here I claim that if I have the identity element, then the A times B, oh, sorry. I was thinking about different, this one says that right inverse is left inverse. So this means if I have two elements that multiply to identity, when B is the inverse of A, then it actually commutes. Then I can actually flip the product, that I can do B times A and I'll still get the identity. In abelian group, this would be for granted, right? But in non-commutative group, this is non-trivial, right? Or almost non-trivial. So how do we prove it? Well, we just use these defining properties of the group and then rules of mathematical logic to derive that. So let's see how this proof is constructed. Let me try to not to screw up the logic, which is sort of easy. So what I need to prove is that B times A will be E, right, the identity element. And what I know is that A times B is E. So this is my assumption, and this is what I need to prove. So what I will start with is that B times A, I know that's an element in the group, right, because I assume that B and A were in the group. And it must have an inverse element, right? That's one of the axioms of the group, that anything in the group has an inverse, right? Sounds funny, but I can certainly do that. So that means that if Y is my inverse of B times A, then I can write that identity is B times A times Y, right? Now watch this. Because E is an identity element, I can multiply this B with the identity, right? That's the second step, and it's certainly equal because multiplication by the identity just gives me the element back, right? And now, what happens next? Oh yeah, here I use the fact, my assumption that A times B is identity. So here I replace this E with A dot B, okay? The next trick is, or next step is to apply associativity of the group multiplication. So this, the order of the brackets doesn't matter. So I can write it also as B times A times another B times A. But I assume that Y is an inverse of B times A, right? So this will reduce to an identity element, and same thing here. So, or same thing. Identity element times B times A is B times A. So all of a sudden, I see that B times A indeed is identity element. That's what I wanted to prove. It's sort of weird, but that's how proofs look like. It's a sequence of logical steps. I think if you stared into it long enough, you would develop some sort of intuition. I did not stare into it long enough, but I think there might be some sort of more intuitive reason behind this. But you cannot beat the logic, basically. You just apply basic logic principles and these axioms of the group, and you just get this is the case. So we can write it either this way, like in this special case, when A times B gives me identity, I can commute, I can flip the order, or if I denote my inverse as A inverse, that's basically this. And after I show you that the group of invertible matrices, that invertible n by n matrices form a group, from this will immediately follow that for matrices this is true, right? And that's the identity. We'll get there in a second. So let's take a look at another property. This is the one you were asking about, Max, right? So that's the one saying that indeed, even though the definition, again, definitions is something you just need to remember in mathematics. No arguing about that. So the identity element I define while multiplying from the right? And here the theorem says, or light theorem or lemma, I guess, is that an identity element multiplied also from the left gives me back the same thing. So it doesn't matter if I multiply from the right or from the left, right? The definition guarantees that multiplication from the right gives me the element back, but also multiplication from the left. So how can I prove it? Well, the trick is to write the identity as A dot A inverse, right? Which I can do because for any element A, I can do the inverse. And when they are multiplied, they give me the identity, right? Associativity, can flip the order of multiplications, right? And A inverse A, that's identity, so that's A, right? So indeed, multiplying from the left with identity gives me that element back. So indeed, doesn't matter if I multiply from the left or from the right. And by the way, think about it, we had all these examples of groups, right? And this was just still just the tip of the iceberg. So now we have proven it in all these cases, these properties, right? In most of them it would be trivial, but the point is you don't really have to think about them separately. Applies uniformly to all of them. Okay, another one. Very relevant to matrices too, as we will see shortly. So that the identity element is in fact unique, that there cannot be two different identity elements. So I guess the proof could go like by contradiction, I guess, if you want to make it more dramatic as a proof. So assume there are two different identity elements, and because both of them, I assume that both of them are identity, right? So both of them, if they multiply something, they just give me the something back. Due to the previous theorem, we know that the order doesn't matter. So if I do A1 times E2, sorry, E1 times E2, I can flip it. That's what I showed before, because it's the identity, so it gives me the identity back. Here it's funny because I have two identities, so it doesn't really even matter. And because E2 is also the identity, then this is also equal to E1, right? So from this follows that E1 is equal to E2. So I guess here I have a contradiction if I assume that they are different, that they are not different. I guess the contradiction is here not necessary. It's just dramatizing the proof, I guess. Okay. So this was uniqueness of the identity element. So there is only one identity element in each group, interestingly enough. And also the inverse is given uniquely. That's sort of good to know, right, in the group. So the theorem says that for every element in the group, it's just one inverse element. Now we know that doesn't matter if I'm multiplying from the right or from the left. In both cases, it gives me the identity. So again, let's try to prove it by contradiction. So let's assume that there are two different inverse elements to A. Okay, so pick some A, and to assume I have its inverse A1 and A2. So both of them give me back the identity element. Okay. Now let's see. What I can do is multiply it with A2 from the left. So I get. So I take this A times. So we put it like this: A times A1 equals E, and I just hit both sides with A2 from the left. Okay, so I get that A2 times A times A1 equals A2 times E. Okay, but this was an identity element, right? So this is A2, right? Here I can apply the associativity, so it doesn't matter in what order I carry out the multiplications. And here, because A2 is an inverse of A, this is equivalent to A dot A2, right? And because it's the inverse, it's E, right? So this is just E times A1, which is A1 equals A2. So what I got from here is that A1 equals A2, so they cannot really be different. They must be the same. Or you could, if you want to be more dramatic, you say this is a contradiction with my assumption that they were different. Got it? I think that it's good sort of to go over this yourselves and sort of think through the logic in your own head. I think that's the only way to sort of convince yourselves that these statements are true. Okay, I think this was enough theorems for today. So let's look at some examples of let's look at the matrix group. So this way I will tie it back to matrices and share what I was promising before. So this is the group that's most relevant to us, and it's the most general matrix group. So the set of all invertible n by n, so remember square matrices, and they must be invertible. And the group operation is going to be matrix multiplication. So the set of all invertible n by n matrices and matrix multiplication forms a group. The group has a name. There's like a whole catalog of group, like an entire zoo of groups. And if you look at it on Wikipedia, like your head will start spinning because the groups are like characterized and they have all sorts of signatures. You can go really crazy about it, but this is the basics of it, which you don't have to go crazy about. So this is the general linear group. That's the name of it. Oops. General linear group, and the n means in n dimensions. It's similar to the notation I used for ON, right? This was my group of orthonormal matrices, so this is like I guess the group theory notation of things. So let's think about it. Let's convince ourselves that this indeed is a group with the operation of matrix multiplication. Okay. So what do we need to, so to make sure it's a group, we need to look at the defining properties of a group, right? All these three basic properties, and make sure that they apply to our case, that they are satisfied, okay? So let's look at the closure. So if I multiply two square matrices, I will certainly get the square matrix of the right size back. That's not a problem, right? But the only thing I need to make sure that I wouldn't get a non-invertible matrix, right? Well, here it's good because if both A and B are invertible, then the product is also invertible, because the inverse is given like this, B inverse, A inverse, right? That's what I started with. And if B inverse and A inverse exists, then certainly this exists too, and I have an inverse of AB, so that's good. So indeed it's closed. So the closure would not be for granted, something you have to actually think about, but in this case, fortunately, it is satisfied. Associativity, that's easy because that follows from matrix multiplication associativity, right? So indeed the group multiplication is associative. What about the identity? Well, I guess I should have let you guess what was the identity, but here it's simple, right? The identity is the identity matrix. It even has the same name, the identity element in the group, the identity matrix. But do you see the difference? Do you see like that the hat the identity matrix is now wearing is like the group theory type of hat? And of course, if you multiply, here I even need only from the right, right? And it's interesting that the group theory itself would tell me that then it applies also from the left, right? So certainly if I take any matrix and I multiply the identity from the right, I'll get the matrix back, right? I assume I don't have to convince you about that. Does everybody has developmental picture of matrix multiplication to see that if you do the identity there, then the ones hit the first column and so on, so that indeed is the case. Is that the case, or shall I draw to work on our? I assume that's a yes. And finally, so that's the identity element, that's the identity matrix. So ones on the diagonal, zeros everywhere else. And the inverse, well, that's the inverse matrix, right? So let me, I guess, remind you, how do we construct the inverse of a matrix? How can we, for an invertible matrix, how do we find it? So let's talk a little bit about this. So I said the matrix inverse is defined exactly so that the matrix, so that the general linear group was indeed a group. So and the matrix inverse was an inversion in that group, right? Because that's I is my identity element, and the matrix inverse is exactly the group inverse property. So how do I compute the inverse? I briefly discussed it the last time. So how do we do it? If I give you a matrix, how can you compute the inverse of a matrix? Well, we need to find a matrix B, right? Or let's call it X, AX, such that I get identity, right? And I can write it out like this. This is my A. I can put my X1, X2, X3 here. It's still 3 by 3. 3 by 3 in this case, and that equals 3 by 3 identity. 1 0 0 0 0 1. Oops, too fast. Is it legible? Yeah. So I think I mentioned before that you can just split it into individual matrix vector products, right? Because if you have an equality between matrices, there's a product of two matrices, you can just look at it as a bunch of equalities between the individual columns of the matrix, right? So this is equivalent to saying I'm solving for x1 such that ax1 is the E1, the first standard basis vector. This would be E2, would be E3, not to be confused with the group identity elements. Sorry about the notation, but that's the standard notation here. And this is just a solving linear system, right? And I assume that the matrix is invertible. That means that this system has a unique solution, not for granted, but that's why I had to assume it. And if I do this, I get these solutions. And if I just put the solutions into columns of a matrix, this is my inverse matrix. So that's how I find the matrix inverse. Is that clear to everybody? Sounds good. So what is the thing is that it's not for granted that the matrix inverse. I was sort of saying that I assume the matrix is invertible, right? You could be asking, how do I know that the matrix is invertible, right? I told you some examples of matrices, the simplest being all zeros. There's no way I can possibly invert it. So how in general can I detect if the matrix is invertible or not? I think I sort of mentioned it very quickly last time, but let me elaborate on that a little bit more, just so you know how to decide if the matrix is invertible or not. So how we can do it, there's multiple ways, but the way we already know is to run Gaussian elimination with row scaling and partial pivoting, the same thing you were programming for your homework that was due yesterday. And if you get all pivot elements, what were the pivot elements? Can you remind me? So the Gaussian elimination converted it to upper triangular matrix, right? Or LU, lower and upper triangle matrix. Let's talk about the upper triangular one. So that looked like this. So there was an upper triangle. There was some elements on the diagonal which could be non-zero. Some bunch of zeros here, lower triangle. And there were some other elements that were non-zero here, right? And these elements on the diagonal, they are called the pivots. And they are important because by looking at the pivots, I can tell if the matrix is invertible or not. So if all the pivots are non-zero, it means that the matrix is invertible. If there is just one zero somewhere among the pivots, that means that I cannot invert the matrix. You want to see why? Like, let's see, for example, take a look at this. So here are my pivots, and let's say that this pivot guy is 0, okay? Just an example. So there might be some other values here. I don't know what they are. There can be zeros, non-zeros. Here are totally zeros, right? And when I will be doing my back substitution, when I will be doing x1, x2, x3, x4, x5, so I'll be solving against all the basis vectors, right? In this case, there'll be 5 of them, right? The moment I will be looking for this guy, I'll get in trouble. When I will be looking for this one, I'll get in trouble, because from this I will find that x5 is 0. Here I will substitute back, I will get that x4 is 0. And here I'm in trouble because here I'm asking for 0, x3 equals 1, right? There's no way on earth to satisfy that. So this one will not have a solution, and that's why the inverse cannot exist. And the reason is this 0 pivot. That's the 0 element on the diagonal. Okay? Same way, if you flip the argument, you can say if all the pivots are non-zero, then the back substitution is going to succeed. So for any column, for every standard basis vectors, this computation, the back substitution is going to succeed, and I can compute the column, and I can get the inverse. Okay? So this is if and only if. That's what I mean by necessary and sufficient condition. So that's one way we can detect that the matrix is invertible. There's other ways to do that. Once we talk more about the determinant, you will know that you can tell if the matrix is invertible by looking at the determinant. And if the determinant is 0, it means it's singular. If it's non-zero, it's invertible. We will get there later. Oh, by the way, you can also, when you are doing this like in MATLAB or like working with some real data, with matrices corresponding to some real data, you can run into all sorts of funny issues that maybe this guy will not be 0, but will be like something like 10 to minus 16. And then you are like scratching your head, shall I really divide by that large number? Or shall I declare it's already singular, right? There's no great answer to it, depends on your particular problem. And here is the most beautiful thing, matrix groups, and in particular subgroups. So maybe let me first tell you about what subgroups are, because it's beautiful. It gives you it's a beautiful structure to groups actually. So if I have a group G? So let's assume that G is a group with my multiplication operation, and I say that a subset of G is a subgroup. Or do I have it there? I swear I had a slide for subgroups, but maybe it went away, so I will just explain it here. So a subset of the set G, subset of the elements, is called a subgroup if S is a group by itself. If all the axioms of the group are satisfied just on that S. Okay? So for example, what would be a good example? Well, let's see about trivial examples, right? So for any group, can you immediately tell me some subgroups? So you have the set of elements, right? Your numbers or whatever, or matrices or whatever you are computing with. And I want to get a subset of it, which will be grouped by itself. So the important thing there is the closure property, right? Because what I need to have is that for every element S1 and S2, so again, I just use this as a shortcut for each S1 and S2 from S, it must be true that S1 times S2 is also from the subgroup. That I don't run away from the subgroup, run out of the subgroup to the G or even somewhere else. I guess I should be saying subgroup with respect to the same group multiplication thing. Also, that must be true, I mean, I can just repeat all the group properties, right? That for every element, I guess, let's say S1 from S, there must be some S2 from S, such that S1 times S2 gives me the identity element. Well, guess what? The identity element also has to be in S, right? But that's just basically saying that the S must be grouped by itself. So if I give you an arbitrary group, can you immediately tell me some examples of subgroups? And I will give you a spoiler. There are 2 trivial examples for any group. Trivial. Embarrassingly trivial. It's funny to think about things so abstractly, right? Like, let me give you a concrete example. So let's say that my group was this 1, 2, 3, 4, with multiplication modulo 5 being my group operation. So what is two trivial examples of subgroups? When you will hear it, you will be like, oh, it's so stupid. Yeah, the identity itself, right? So just one trivial subgroup, right? The identity that you won't get anything, you won't get any smaller than that, right? That's the smallest subset. That is a subgroup, right? Because in every subgroup there must be the identity. I guess I should put X is identity in S. So you cannot get away of it, but the identity turns out to be sufficient because identity is perfectly happy. It's identity, and the inverse of identity is also identity. So that's a perfect subgroup. The other trivial example is even more embarrassingly simple. Yeah, it's the thing itself. Yeah. So those are 2 trivial examples, but the interesting, I guess it's sort of like silly, right? Like if I ask you, what is the solution of this system of linear equations? By the way, we will be doing this next lecture. But if I write a system of linear equations, I don't have to tell you what the dimensions are. Just trust me that the dimensions match. Can you immediately tell me a solution think you can. Oh? 0. Yep. Trivial solution, right? But so those are the trivial cases. So we need to rule them out because what we are interested in are the non-trivial cases, right? It turns out that matrices, matrix groups, this general linear group, the GLN, has lots of interesting subgroups which are not trivial. So if I said, what are the subgroups of GLN? You could immediately say, well, just the trivial ones, right? But here are some non-trivial ones. So the group of matrices with orthonormal columns. So let's try to be a little pedantic about this. I was saying so the rows or columns doesn't matter. So let's try to make it more precise. So let's say I define the group ON as a group of matrices with orthonormal columns. Okay, and I claim this is a group and not just any group. It's a subgroup of GLN. Okay. So how do we convince ourselves that that is indeed the case? Let's see. Well, so let's see. So I need to show that for every A and B from ON, that A times B will be also orthonormal, right? Meaning having orthonormal columns. So what does it mean for a matrix to have orthonormal columns? So let's see if I get it right. So that means that ATA is identity, right? Because let's see if I can get it right. At this point, it's usually getting too late. I'm getting tired and I'm doing mistakes. But let's see if I can get it right this time around. Okay. So I was talking about columns. So so in the transpose they will be rows, right? So those the A1 up to AN are columns of my original matrix. And if I do ATA and I require this to be identity, okay, and then round of paper, then that's yeah. So this is basically saying that the columns of A are orthonormal. Everybody sees that? So let's see if you can get this right. So I want to show that A and B will also have orthonormal columns. So I guess what I have to do here is to do AB transpose. That will be easy. So I need to show that AB transpose AB is identity, right? But this is, we know the rules. We know that this is BT, AT, AB, right? From associativity, I immediately have BT, ATA, I can put the brackets like this, right? But ATA, I assume that A has orthonormal columns, right? So this is identity, so this is BTB. But B, I also assume it has orthonormal columns, so that's the identity, right? So indeed, the product also has orthonormal columns. So indeed, the closure property holds, okay? Ah, that's the thing. Okay, we know that for orthonormal matrices, the transpose is equivalent to the inverse is equivalent to transpose, right? Because this, when I inverted the matrix, I got the inverse matrix, right? So we know that AT, or better said, A inverse is equivalent to transpose, right? Now, because it's a group. So I guess what I'm trying to show you now is that from the fact that the columns are orthonormal, we can also get that the rows are orthonormal. I was previously like a little sloppy about it. I was like saying it doesn't matter. Here I'm trying to show you why it doesn't matter, okay? And specifically I'm trying to show that if a matrix has orthonormal columns, it also means that it has orthonormal rows, okay? So for orthonormal rows, I would need this. I would need AAT equals identity. Let's see if your matrix multiplication brain center is developed enough to see this. Do you see that this matrix equality is talking about multiplying pairs of rows and requiring them to be orthonormal? It's a similar idea like this, right? Except that it's the other way around. Because here I'm looking at a row of A and a column of AT, but a column of AT is a row of A, right? So this is indeed talking about rows. So this one was saying that the columns must be orthonormal. This equality is saying that the rows are orthonormal, right? And I want to show that from this one follows this one, okay? But here it's simple because here is what I can do. So if this is true, if I have orthonormal columns, then I can use the fact that the inverse is the transpose. And I know due to the group properties is that I can flip this, right? And this is still going to be transposed. So this, I wanted to show this, that AAT is identity. So indeed, orthonormal columns imply orthonormal rows. And that's why you actually can be sloppy about it, because it doesn't matter, because one implies the other one. You could also flip the logic and show that from orthonormal rows, all orthonormal rows imply orthonormal columns, of course. Okay, so this was just a long discussion of the group of orthonormal matrices, which is a subgroup of the general linear group. Okay. Notice that identity is there, right? Notice that if you do the inverse of an orthonormal matrix, you get an orthonormal matrix. That's exactly why, right? If you because inverse of an orthonormal matrix is transpose, right? And I just showed that orthonormal columns are equivalent to orthonormal rows. So if I do inverse of an orthonormal matrix, it will be still an orthonormal matrix. Okay, another example of a matrix subgroup is a group of matrices with orthonormal columns and determinant 1. So, by the way, we don't have to talk about columns or rows anymore. We just talk about orthonormal matrices. If they are square, doesn't matter. We will need to make a difference between orthonormal rows and columns when we'll be talking about rectangular matrices, but we can save that for later. In the case of groups, we always have square matrices, so we can be talking about the inverse. So the group of matrices which are orthonormal and have determinant 1, that's a very important group of matrices called special orthogonal group. So this SO stands for special orthogonal. By the way, don't be confused by this terminology. This all means, some people say, you will find it even in books and so on, orthogonal. But what it really means is orthonormal. It's just that the orthogonal already implies that the norms of the rows and columns are 1. Okay, so that's just a terminology thing. It still means orthonormal. So SON, that's the group. What is the other name for the group of SON? I think I've been talking before about SO2, SO3 in 2 and 3 dimensions.
Rotation.
They are rotations, exactly. So this is one way how you can say, I want a proper rotation, not a reflection, right? Because orthonormal matrices, as I said in the beginning of the class, they are both rotations and reflections. But the special orthogonal group, it's just rotations. Very important, like in robotics and all these, wherever you simulate some system of rigid bodies, the rigid bodies can only be transformed by elements from SON, only by proper rotations, because reflection, impossible to do reflection to actual body, right? Like my pen, I can rotate it all the way I want. I have no idea how I could reflect it, unless I had some superpower, which I don't. So a group of invertible lower triangle matrices is also a group, because we had, remember we talked about LU decomposition, when you multiply 2 lower triangles, you get a lower triangle. And if you invert a lower triangle, you get also a lower triangle. So indeed, this is another beautiful example of a subgroup. Yep. Same thing, of course, not surprisingly, holds for upper triangular matrices. And permutation matrices, remember what were permutation matrices? Who remembers what we're? I guess you're also getting tired, not just me. It's getting late.
Oh, it's just like identity matrix, but the rows are swapped.
Oh, that's a very nice way to put it. So let me repeat it for the record. That is just an identity matrix with arbitrarily swapped rows or columns, by the way. And the beautiful thing is that the group of permutation matrices is actually a subgroup of ON, right? Because all permutations are orthonormal. That's trivial to see. I think we talked about that before. But not all orthonormal matrices are permutations. Now, permutations are not a subgroup of SON because some permutations can actually have determinant -1. And that's what will be important when we'll be talking about determinant. That's how determinant will be defined for general matrices. All right, so the grand conclusion here, unless you have some questions to this. You don't look like you do. So the group theory immediately gave us these useful properties for invertible n by n matrices in group language GLN, general linear group in n dimensions. I mean, this A times identity is identity times A, that follows directly from the group properties. It would be easy to just see it directly, but the cool thing is it follows directly from the group properties. Now, what also follows is that the identity is unique. So there is no other matrix which multiplying another matrix would give me that matrix back. The identity is unique. Again, follows from the group structure. The other thing we have seen is that matrix inverses are unique. Good to know that, right? And as I was saying, that the right inverse is left inverse. Another thing we get immediately from the groups. And the groups are nice because they don't apply just to matrices, but, and by the way, this would also apply to all the subgroups, right? Not just GLN. I could say the same for ON and so on. I guess it's sort of obvious. Okay, so that's the end of my group theory, elementary group theory lecture. You can study group theory for like an entire semester, and you can have advanced group theory for another semester. I didn't even go that far. It's useful like in particle physics and so on. People go like really crazy about it. So apparently that has some real implications in nature, spin groups and so on. So it's an exciting subject, but this is all we will do here. Okay? Thank you.